Hi, everybody. This is Elif Ozkirimli. I'm the head of data science at Pharma International Informatics at Roche. And it's my pleasure to be joining you today at the NLP Summit Healthcare to talk to you about the opportunities and challenges of using natural language processing for biomedical texts. So today I'll briefly mention how natural language processing in healthcare and in our domain, how we use it. Then I'll go a little bit deeper into an internal capability that we have built that provides an opportunity for all of us to collaborate. We call it the NLP Engine, Natural Language Processing Engine. Then I'll briefly describe one of the use cases that we have on healthcare professional or HCP feedback classification. And as I promised in my title, I will then wrap up with some of the challenges of working with biomedical text and especially with imbalanced data and how we approach these challenges with some research approaches. Okay, so we have reached a pivotal moment in healthcare, and I don't need to tell you that the convergence of science and technology offers new opportunities. So we have more data that provide a deeper understanding of the patient journey. We have better technology that offers new ways of collecting data and enhancing care. And the advances in machine learning methodologies provide new insights that we can derive from this data and technology. And a combination of data, technology, and machine learning advances provide opportunities to improve patient outcomes. And this is what I mean when I talk about this pivotal moment in healthcare. But unlocking the potential of machine learning requires that we have access to large data sets. And these large data sets, as machine learning models become more complex, these large data sets need to be also annotated for higher accuracy. But the scarcity of annotated data limits the use of supervised learning. So the challenge is to improve the efficiency of supervised machine learning approaches by improving the efficiency with which we derive insights from the available labeled data. Because manual data annotation is laborious, time-consuming, and requires specialist expertise, approaches beyond supervised machine learning can unlock some the potential of machine learning. And if we can overcome this challenge, we can improve the scalability of machine learning approaches in biomedical applications to help make our vision for personalized healthcare a reality. Okay, as a part of this large data sets that we have access to, today we're going to talk about natural languages, the data set collected in the form of text, not only because this is the NLP Summit, but also because a lot of the data that we do collect in the biomedical domain is in the text form. And they can be in the form of natural languages, English, Spanish, Chinese, etc. They can be DNA sequences, protein sequences, chemical formulae. And you see that these languages are very context-dependent, terminology-rich, and very specific. So these create some challenges for processing these types of data. But apart from that, there's another challenge in the fact that some of the interesting information is in fact not sampled enough. So the amount of information for these rare events is not sufficiently sampled because the whole knowledge space is not accessible sometimes, and therefore data scarcity becomes a challenge. So I will also mention some of these challenges in my talk today. So in our section, we have been working on these natural language processing use cases to understand the customer, which is the healthcare professional most often, to fulfill their unmet needs. Some of the use cases that we have received are, for example, search in PDF documents using fuzzy matching, scientific literature search by relevance ranking or information retrieval, healthcare professional feedback classification, which involves multilabel classification as well as sentiment analysis, or record matching, or through non-semantic matching. So these use cases, as you see, are all based on text or unstructured data. And similar steps are performed repetitively with minor changes, such as parsing or pre-processing. So we thought a modularized approach will speed up rollout and minimize effort. And furthermore, we wanted to co-create interpretable, explainable, and more accurate solutions with Roche subject matter experts. So to be able to achieve these, the modularized approach and also these interpretable, explainable, and more accurate solutions with Roche SMEs, we thought we would first examine this common pipeline that we have. And we see that the common pipeline can be divided into these modules that can be reproducibly used or reused for scalability. But furthermore, we could also focus on some of the recent advances in natural language processing to be able to use pre-trained models, fine-tuning, and as well as active learning, both to achieve state-of-the-art, but also co-creation with subject matter experts. So what we needed was a comprehensive Python-based library for data scientists, an interface to high-performance computing, a home for NLP data scientists with easy-to-use package with state-of-the-art performance on models, and a platform where data scientists can train, store, and use robust NLP models. So this was what we needed, but we also had a dream. Our dream was to achieve scalability, speed, and reproducibility. This I already mentioned, by reducing model building time for scalability, ensuring reproducibility and robustness, and improve standard benchmarking capabilities. But our dream was also to provide a seamless and cool user experience with cross-platform functionality. We also wanted to connect the Roche data science community to create value with a shared purpose. And to complete the cycle, by building this internal capability for open sharing, we were able to enhance our research capabilities as well, to develop new models and architectures and deliver state-of-the-art models for Roche-specific use cases. So our pipeline for the natural language processing engine looks a bit like this, where we use an validated internal coding environment that is open to the Roche community on an end-to-end data platform to perform some of these NLP or natural language processing tasks, such as classification, text similarity, sentiment analysis, etc. So bringing together the code for these tasks for reusability. And I mentioned to you about best practices. We have a strong focus on best practices for FAIR criteria, where we work on the NLP engine capabilities also inform the best practice build, the capabilities for best practices by focusing on coding standards, best practices in coding and development, FAIR data standard, making NLP-related data, information, and insights fair, and efficient technical integration with minimum refactoring effort and CI/CD pipeline, as well as a cross-platform capability. So the NLP engine was informing our best practices within our team, but the best practices effort was also informing our NLP engine capabilities as well. So the natural language processing engine, or NLP engine, has 3 layers of capabilities. So the first layer is that it's a powerful and state-of-the-art NLP library, but it's also a biomedical vocabulary library, and it is a Roche customized text embedding library, so that we could deliver some of these Roche-specific use cases that do require subject matter or Roche-specific expertise. So if I was to describe to you one of the use cases that we have been working on, this is called, we call it healthcare professional feedback classification. This is an example use case, just to highlight how do we use the NLP engine to accelerate scalability. So if I was to describe the approach, the feedback is received from the healthcare professionals, and then here Lisa manually checks all healthcare professional feedback each month. She splits free text feedback into several sentences based on her experience. Then she classifies each sentence to say if it's insight where Roche can take action, or not insight, not relevant for Roche. And then the insight sentences are classified into 7 areas. So you see that this is first sort of a binary classification, but then a multi-class classification problem where there are 7 classes for the insight sentences. So this is sort of the business case where Lisa spends 2 days on this task every month. So the challenges of working on this is that it requires manual effort. It's time consuming. Most often there's an external agency that's involved, so it involves cost. And furthermore, which I will mention also in a little bit, it can lead to inconsistent classification depending on who classifies, who does the classification. So we built a data pipeline where we start with data ingestion, we train machine learning models, we predict the classes, and then we build a customized dashboard where business can visualize model predictions for the healthcare professional feedback classification use case. But one challenge remains, and I mentioned to you about this inconsistency. It's hard to annotate data consistently. So on the left-hand side, you see cats, and it's relatively easy to label these as cat. And on the right-hand side, you see not cats, and it's relatively easy to label them as not cat. But what about the ones in the middle? It's not straightforward to annotate data consistently, and sometimes you need context or subject matter expertise to be able to do this. Of course, here I'm showing you a toy example. With biomedical text, it requires subject matter expert input. And therefore, we included subject matter expertise by human-in-the-loop machine learning or active learning, where the subject matter expert gets involved for the low confidence cases to correct the mislabels or add to labels to unlabeled feedback. So I hope I was able to briefly talk to you about this HCP feedback classification that is powered by our NLP engine, and to show to you that we provide a state-of-the-art machine learning models continuously improved by active learning. This is now scalable for different number of labels and amount of data, again, powered by this scalability that is provided by the NLP engine. It supports more than 20 different languages. It is fast because it's automated, and also there's no need to pay an external company for labeling. And this, of course, also frees up time for the subject matter experts to focus on more value-added tasks. So this was a classification use case that I talked to you about from one of our use cases. And I also mentioned to you that I would talk to you about the challenges of using natural language processing approaches. And the text, as I mentioned to you, text data in the biomedical domain, when you have access to this, finding the relevant information is not so straightforward because it becomes a needles in a haystack problem. Sometimes there are only a few examples of the information that you need to access. And furthermore, finding the needles in a haystack is even more challenging for multi-label text classification. Here I'm showing you what I mean when I say multi-label text classification. On the left-hand side, you have an abstract from a paper. And on the right-hand side, you see the labels that are associated with this abstract. And you see multiple labels that are associated with this text. And you can also imagine, I hope, that some of these labels are going to be occurring more often. For example, COVID-19, right? So there has been an explosion in COVID-19 related literature, or humans. So this is another common, this is going to be another common label. But for example, intensive care units, organization and administration will probably be a more rare label compared to the ones that I just mentioned. And finding those rare labels may be what you are most interested in sometimes. So if we examine these, a subset of PubMed documents, here the subset, the data set comes from a previous challenge that we also participated in, where PubMed articles are provided with titles and abstracts. And the number of documents in this specific data set was around 200,000, where there were 18,000 labels, and the average number of labels per instance was 12, and the average number of instances per label was 151. But it's not the averages actually, but it's the distribution of how the labels are available within the text. So if you look at this graph where I plot number of articles versus sorted label index, you see that there's a long tail for this distribution where some of the labels have many articles associated with them, while some of them have only a few. And furthermore, there will be co-occurrence. As I mentioned to you in the previous slide, the intensive care unit label may be co-occurring with a very common label, such as COVID-19, and this might also lead to more complication or challenges for this multi-label text classification task. So loss function manipulation has been proposed as an approach to address class imbalance and has been used previously as well, of course. For example, binary cross entropy is a very commonly used approach, but it's vulnerable to label imbalance due to dominance of head classes or negative instances. Resampling and reweighting is another approach, but these are not effective when there's label dependency, as I mentioned to you about this label co-occurrence, because they result in oversampling of common labels. So we proposed a novel approach using distribution balance loss with 3 layers: focal loss, rebalance weighting, and negative tolerant regularization. And we tested our algorithm or our approach on both a biomedical data set as well as a news data set. So we tested distribution balance loss on the PubMed data set that we had to show that even for tail labels, the distribution balance loss improves classification performance. So if we examine this table very quickly, here I'm showing you the total performance for all of the labels with micro F1 comparison. And you see with distribution balance loss, even the performance for all of the labels increases compared to some of these support vector machine or binary cross entropy baselines. But when you look at the tail labels, for which there are only a few examples, meaning less than 15 examples, the support vector machine or binary cross entropy does not perform well or at all, while our approach achieves high performance compared to these baseline methodologies. And this was recently published in NLP in 2021. Another approach to handle rare classes was to combine in this ensemble-like approach, a hybrid approach, complementing rare classes with synonym matching as well as NER to learn the frequent context. So if a label is rare, we use name density recognition or synonym matching to come up with the label of interest. And this for this one, we participated in the BioASQ challenge for semantic indexing for biomedical articles in Spanish, and achieved high performance in terms of precision and accuracy as well. So to summarize, I hope I was able to talk to you a little bit about some of the challenges, but also opportunities that take us beyond supervised learning. And recently we published this review article where we summarize some of these approaches to handle this labels in a haystack problem, where semi-supervision, active learning, which I already mentioned, data augmentation, transfer learning, self-supervision, or weak supervision can be used to achieve high performance, even in the lack of annotated data sets. So the 3 takeaway messages I have are that Our NLP Engine framework provides scalability and reproducibility. So this modularized approach was helpful for us in delivering some of these use cases by following best practices. I talked to you a little bit about these approaches beyond supervised learning that can unlock the potential of machine learning by helping find needles in a haystack. And I hope I was also able to talk to you about how this collaborative or open source and open science mindset was able to propel our data science team by helping us focus on research questions as well. Thank you very much.